So recall that we have defined the logarithm as the integral of 1 over t. The exponential is the inverse function, and we've proved some results about the functions log and exp. And we've defined e to be exp of 1, and we're now going to talk a little bit about defining a real number to an arbitrary real power. We define x to the a. Recall, we define x to the a as exp of a log x. We talked about this last time. And now we're going to check and make sure that all the usual properties we expect to be true are indeed correct. So here is a proposition. This is basically to make sure that this new definition of powers coincides with the definition we're used to when the power happens to be an integer. So let's let x be a positive number, n be a natural number, and a be a real number. And then, so first things first is that x to the power of 1 is x. And x to the power of n plus 1 is x to the n times x. And then by induction, x to the n for any integer n is x multiplied by itself n times. So if the power is an integer, then x to the n is what we expect it to be. Second thing is that the nth root of x to the n to the power of 1 over n, that's the same thing as the x to the 1 over n to the power of n is also x. So now fractional powers really are nth roots. And the third thing we're going to check is that the logarithm of x to the a is a times the logarithm of x. And the proof of this comes pretty easily from the definition. So part A, x to the 1, that's defined as exp of 1 times log x. Then 1 times any real number is just itself. So we've got exp of log x is just x, because exp is the inverse of log. And then x to the n plus 1, that is exp of n plus 1 log x. That's exp of n log x plus log x. And as an exercise, you prove in theorem 3.3.4, this is the exp of n log x times the exp of log x. And that's theorem 3.3 or C. And that, by definition, is x to the n times, we saw before, x. So we have that integer powers do indeed match up with what we'd expect them to be. And then part B, let's take x to the n to the power of 1 over n. That is exp of 1 over n times the logarithm of x to the n. And we haven't proven part C yet. We can't move arbitrary powers down, but we did see that you can move integer powers down. That is theorem 3.3.2c. And we just cancel out the n with the 1 over n. We're left with x log x, which is just x. Other direction is a smidge trickier. X to the 1 over n to the n. That is x of n times log of x to the 1 over n. That's x of n times the log of. Now this is tricky. X of 1 over n times log x. Now because n is an integer, we can move that x log, and then that thing, x 1 over n log x, that whole mess to the n. And that we can move it integers into exponentials. And now we use a corollary to theorem 3.3.4 or c, exponential to the power of n, the x log hang out front, and then that becomes x of n times 1 over n log x. That is by theorem 3.3.4c. And then, as usual, we just cancel out the n and the 1 over n. X log, X log. Doesn't matter how many of them we get at the end of the day. We get an x. So that's part C. So now we see that that nth roots do what we think they ought to do. Then part C follows directly from the definition. Logarithm of x to the a, that's the logarithm of x to the a is x of a log x. And then the logarithm cancels with the exponential because they are inverse functions to each other, and we're just left with a log x. That is all there is to that proposition. The following proposition is left as an the proof is left as an exercise to the reader because it's kind of boring, but you can check that all the usual properties of exponentials are still hold. So sum in the power becomes multiplication outside. Product, you can distribute an exponential over a product the way you can distribute multiplication over a sum. Powers, two powers, you get it is just multiplication of powers, and subtraction in the exponent is just division. Now let's say a bit more about the number e. Recall we it defined that E is the exp of 1, and then here is a fact, a straightforward proposition. E to the x is exp of x log e, but since e, exp, and log are inverses of each other, this is just exp of x. So the function exp is indeed just e to the x. One quick proposition about differential equations. There are much more general versions of this theorem floating out there, but this is good for our terms. Let's let f be a function whose domain is, say, an open interval. And let's suppose that f prime of x is equal to f of x for all x in the domain, in this interval. Then there is a constant c, a real number c with such that f of x is c times x of x. So x of x prime, we saw in the last video that the derivative of x is itself. What this proposition is saying to you is that x is the only function with this property. And the proof is fairly straightforward. So let's take f over x prime by the quotient rule, f prime x minus f x prime over x times x. But then because f and x are both their own derivatives, this is just 0. So by corollary, 2.3.6, f over x is constant. And then you just let c be the constant value of f over x, and you do a very little bit of algebra. By corollary, 2.3.6, f over x is constant. And then you just let c be the constant value of f over x, and you do a very little bit of algebra. Now let's recall if b is positive and also not equal to 1, then log base b of x is defined to be log x divided by log b. And then a proposition that this is indeed what we think it should be here is that if x is a real number, b is positive and not equal to 1, then b to the log base b of x is x, and log base b to the x is also equal to x. So this is saying that log base b is the inverse of the b to the x function, as we'd expect it to be. And the proof of this is pretty straightforward. B to the log base b of x, that's exp of log base bx times log b. That is to say exp of log x over log b. Log b. Then just cancel the logarithms of b, cancel exp with log, and you're just left with x. And conversely, log base b, b to the x, that's log b to the x over log b, 1 over log b. Then log b to the x is log exp of x log b. So the log and x cancel with each other, and we're just left with x times log b over log b. The log b's cancel with each other, and we're just left with x. So these definitions do match up with what we think they ought to. And then the following proposition tells us that logarithms to the base b have all the properties we think they ought to have. So let's let b, x, and y all be positive numbers. B is not allowed to equal 1. Then, first off, logarithm of a product is the sum of the logarithms. And this is an exercise to check that these are indeed correct. Log of a quotient is a difference, and part C is that if A is a real number, doesn't need to be positive, then logarithm x to the A is A times a logarithm of x. Here's another proposition that's a little bit more interesting and might tie into some definitions of E you might have seen in the past. I know this is how I first saw the number E defined. Let's let A be a real number and let A sub n be the number 1 plus A over n to the nth power. Then an is a sequence of real numbers. And notice that all we have to do to define an is we need to be able to divide a real number but an integer, add 1, and then take it to an integer power. So what we're going to write down, what I just wrote down, doesn't rely on anything we've done in this section. I could have defined these ANs all the way back in section 1.2. So the interesting thing, of course it's a sequence that convert, but the interesting thing is that it is a convergent sequence, and I can tell you what it converges to. The number exp of A, also known as e to the A. Convergence in the sense of definition 1.3.1 or proposition 1.3.3a. Now, the proof of this will, of course, require dealing with exponents and logs, but that shouldn't surprise you too much. If you're going to prove it's equal to exp, you're going to need to use some things about exp. So let's let f of x be a logarithm of 1 plus ax. And let's let g of x be x. Then, not the number we care about, but its logarithm is f of 1 over n divided by g of 1 over n. That's because you can, of course, move the 1 over n out front. And let me point out to you that f of x exists, and in fact, f is continuous if, let's say, the absolute value of x is less than 1 over the absolute value of a. Now, if a is positive, f of x exists for all positive x. If a is negative, f of x exists for all negative x. F of x exists for all x such that 1 plus x is positive. But I'll just point out that whether a is positive or negative, f of x exists if x is close enough to 0. Or f of x exists for all x. If a happens to be 0, then f of x is just the constant function 0, but that's not really the interesting case. So now, by L'Hopital's rule, we have that, let's write this out, limit as x approaches 0, and it doesn't matter which side we're coming from, f of x over g of x. G of x exists everywhere. F of x exists as long as x is close enough to 0. That is the limit as x approaches 0, f prime of x over g prime of x. And then g prime of x is 1, so I'm not going to bother write that down. The derivative of f of x by the chain rule is 1 over 1 plus ax. And then you multiply by the derivative of the bottom is a. And then taking the limit as x approaches 0, limit of a rational function, as long as you're not dividing by 0, which we're not, you just evaluate the limit by evaluating the function. So the limit is indeed a. Now we need to pass from limits in the sense of chapter 2, which is what L'Hopital uses, back to limits in the sense of section 1.3. So here's how we do this. We're going to use continuous functions, and then we can use the definition of limit in terms of continuous functions. H of x is going to be f of x over g of x if x is not equal to 0, and also f of x is defined so x times a, absolute value, is less than 1. That's true. And it's going to be a if x is equal to 0. And I'll point out to you that 0 is indeed a limit point of the domain of H. So, by a corollary from section 2.1, H is continuous at A. And now, exp is continuous everywhere. So, by a proposition 1.7.4, exp of H is continuous at 0, but exp of H of X, it is exp 1 over x log 1 plus ax. It's just 1 plus ax to the 1 over x and now the sequence 1 over n converges to 0. So by proposition, by definition 1.7.1, we have that 1 plus a over n to the nth power, we have that is indeed converging it to exp of A. We're going to finish section 3.3 by building up to a very famous, very important example of a function, and the first thing we need to do is we need to talk about the limits of exponentials. Now, we already know that e to the x goes to 0 as x goes to minus infinity, but what we need to prove now is that that's still true even if we multiply e to the x by a polynomial. So here's our proposition. If n is an integer, a non-negative integer, so either a natural number or 0, then here is the first part. The first part is that the limit as x goes to infinity of x to the n times e to the minus x, that limit is 0. So even though x to the n is going to infinity, e to the x, or rather e to the minus x is going to 0 fast enough that the whole thing goes to 0. And part B is that as x goes to 0, or let's go ahead and call the variable y in this case 1 over y to the n, then let's write this as exp negative 1 over y. That limit is 0. And now the proof of this is pretty straightforward. We have that, so part A at least, if n equals 0, then that's just the limit as x goes to infinity of e to the minus x is 0 by theorem 3.3.4e. Technically, that is a limit as x goes to minus infinity e to the plus x, but you can prove that it works just fine on the other side by the same technique. Now suppose that we have the results for some x. This is of course going to be a proof for some n. This is of course going to be a proof by induction. Then I'm going to write this way. Limit as x goes to infinity, n plus 1 times x to the n divided by e to the x. That is also equal to 0. And that is by proposition 2.1.11b. You can do multiplication inside a limit at infinity, and it'll still work out. And of course, the fact that the limit as x goes to infinity of the constant n plus 1 is indeed the constant n plus 1. And let's notice that this is the limit as x goes to infinity of a quotient. The top is the derivative of x to the n plus 1, and then the bottom is the derivative of e to the x. So by L'Hopital's rule, technically you have to bring in exercise 2.5.2 because L'Hopital's rule, as stated in your book, is all about limits at a point, and this is all about limits at infinity. But that's okay. We have that 0 is the limit as x goes to infinity, just x to the n plus 1 over e to the x, also known as the limit as x goes to infinity, x to the n plus 1 times e to the negative x. And we can use L'Hopital's rule because x to the n plus 1 and e to the x are both going to infinity. Yeah, so this is an indeterminate form, and in particular the limit exists. So by induction, this is true for all natural numbers, and 0, that is all non-negative integers. Part B involves what's called a change of variables argument in your limit. So let's pick an epsilon greater than 0, and let's let p be a real number, be such that if x is greater than p, then x to the n e to the minus x is less than epsilon, and then by part A, and the definition of limit at infinity, p has to exist. And in fact, we may require that P is, let's say, bigger than 1. If P is less than 1, just replace P by 1. And then, so if this condition is true for all positive x's or all x's bigger than -7 or something, it's certainly going to be true for all x's bigger than 1, because everything bigger than 1 is positive or bigger than -7 or whatever you have. Then we let delta be 1 over P. And then if 0 is less than y is less than delta, then 1 over y is bigger than P. So 1 over y to the n exp negative 1 over y. I'm using exp instead of e to the just because it's easier to write. That is also going to be less than epsilon. And so that is exactly the epsilon delta characterization. So limit as y goes to 0 from the right, 1 over y to the n, e to the negative 1 over y. That is 0. We're actually going to need a very particular special case of this. So here is a corollary. First part is that if n is a positive, a non-negative integer, then we can take this limit with a negative 1 over x squared instead of a negative 1 over x here. And the second is that if P is a polynomial, then instead of looking at 1 over x to a particular power, you can just take your polynomial, evaluate it at 1 over x. This limit, of course, is equal to 0. So let's prove this. So part A, we're going to use proposition 2.1.5b again. Technically, proposition 2.1.5 is limits at a finite point, not necessarily at infinity, but everything in proposition 2.1.5 and 2.1.11 for that matter carries through for limits at infinity. That's not a terribly difficult exercise. So let's consider this function, exp 1 over x minus 1 over x squared. And I'll point out to you that this thing up here, 1 over x to the n times x minus 1 over x squared, that's the thing we know how to deal with. That is this thing here, x is instead of y, is times this thing I have just told you to consider. So that's where that is coming from. That's where we're going with this. And then here's what to notice about this. It's that if x is between 0 and 1/2, then we've got that 1 over x is greater than 2, and also positive, so 1 over x squared is greater than 2 over x, and then you can add things to either side of it. In inequality, you get negative 1 over x is greater than 1 over x minus 1 over x squared. And then since x is increasing, which, recall, is from theorem 3.3.4 or D, we have that x minus 1 over x is strictly greater than x of 1 over x minus 1 over x squared. But then x is always positive, so this is always greater than 0. And now we know what the limit of this part is as x goes to 0. It's just 0. And we know what the limit of 0 is as x goes to 0. That too is 0. We know how to take the limit of a constant. And so its exercise is 2.1.4. This is the squeezing principle. If you have some function that is trapped between two things whose limit is both the same, is both 0, then the thing in the middle must have the same limit. All right, so by proposition 2.1.5, if C, I guess we do only need that at a finite point. We need the variant for one-sided limits. We have that the limit as x goes to 0 from the right, 1 over x to the n, x negative 1 over x squared, we have the thing which we know is 0 from the previous proposition times the thing we have just worked out. Which is 0 times 0 is 0. So that's it for part A. And then for part B, we're going to let our polynomial p, let's call the variable z. You can always write a polynomial sum from k equals 0 to n, z to the k, times some coefficients a sub k. So our limit of our polynomial of 1 over x, and then our x minus 1 over x squared. This is going to be limit as x goes to 0 from the right. Coefficients ak, then 1 over x to the k, x minus 1 over x squared, and then proposition 2.1.5 gives you the sum of the limits is the limit of the sums, and you can move the constant out. So we're left with 0 by proposition 2.1.5 and part A. That is all there is to that.